How I passed the Praxis General Science 5435 on my first try preparation quiz. Question 1. A student is studying the properties of waves and learns about the relationship between frequency, wavelength, and speed. The student knows that the speed of light in a vacuum is a constant. If a beam of light has a frequency of 6 times 10 to the 14th power hertz, what is its approximate wavelength, using 3 times 10 to the 8th power meters per second as the speed of light? Is it? Option A. 5 times 10 to the negative 7th power meters, which is 500 nanometers. B. 2 times 10 to the 6th power meters. C. 1.8 times 10 to the 23rd power meters. Or D. 5 times 10 to the 7th power meters. The correct answer is A. This question requires the application of the basic wave equation, which states that speed is equal to frequency multiplied by wavelength. To find the wavelength, the equation is rearranged to wavelength equals speed divided by frequency. Given the speed of light c is 3 times 10 to the 8th meters per second, and the frequency f is 6 times 10 to the 14th hertz, the calculation is 3 times 10 to the 8th divided by 6 times 10 to the 14th. This simplifies to 0.5 times 10 to the negative 6th, or 5 times 10 to the negative 7th meters. This value, 500 nanometers, falls within the visible light spectrum. Option A correctly shows this calculation and result. Option B and D yield wavelengths that are many orders of magnitude too large. Option C is also an impossibly large number. Understanding this relationship is fundamental to working with the electromagnetic spectrum. Question 2. A student is studying the water cycle and understands the processes of evaporation, condensation, and precipitation. The student asks a thoughtful question. If water constantly evaporates from the oceans, why does it not just accumulate in the atmosphere as an ever-thickening layer of vapor? Which of the following explanations best answers this question using principles of physics? Is it? Option A. The atmosphere has a limited capacity to hold water vapor, and this capacity is highly dependent on temperature. When warm, moist air rises and cools, it reaches its saturation point, or dew point. The excess water vapor then condenses into tiny liquid droplets, forming clouds, which can eventually lead to precipitation. B. Water vapor is actually heavier than the dry air mixture of nitrogen and oxygen, so gravity constantly pulls it back down to the Earth's surface, which is why it rains. C. The rotation of the Earth creates a centrifugal force that flings water vapor back towards the surface, preventing its indefinite accumulation in the upper atmosphere. Or D. The process of transpiration from plants releases so much water vapor that it balances the amount evaporating from the oceans, creating a steady state. The correct answer is A. This question addresses the physical principles governing the water cycle. The key concept is that air has a maximum capacity for water vapor, which is determined by its temperature. Warm air can hold much more water vapor than cold air. As warm, moist air rises in the atmosphere, it expands and cools. If it cools to a temperature below its dew point, the air becomes saturated. The excess water vapor can no longer remain as a gas and must condense into tiny liquid droplets, forming clouds. When these droplets grow large enough, they fall as precipitation. This cycle of rising, cooling, and condensing prevents the indefinite buildup of water vapor. Option A correctly explains this process. Option B is incorrect. Water vapor is less dense than dry air. Option C introduces an incorrect force. Option D describes a component of the cycle, but does not explain the physical limitation on water vapor accumulation. Remember, we can take your Praxis 5435 exam for you remotely and undetected with 150 score guaranteed. Message us via the number in the bio. Question 3. A student is studying basic Mendelian genetics. They know that in pea plants, the allele for purple flowers is dominant over the allele for white flowers. The student crosses a pea plant that is homozygous dominant pp for purple flowers with a pea plant that is homozygous recessive pp for white flowers. All of the offspring in the F1 generation have purple flowers. The student then crosses 2 of these F1 plants with each other. What is the expected phenotypic ratio in the F2 generation resulting from this cross? Is it? Option A. All of the offspring will have purple flowers. B. Approximately 3 purple-flowered plants for every 1 white-flowered plant. C. Approximately 1 purple-flowered plant for every 1 white-flowered plant. Or D. Approximately 9 purple-flowered plants for every 7 white-flowered plants. The correct answer is B. This question tests the understanding of a classic monohybrid cross. The initial cross between a homozygous dominant pp and a homozygous recessive pp parent produces offspring that are all heterozygous pp. Since purple is dominant, all these F1 plants have purple flowers. When 2 F1 heterozygotes are cross pp times pp, the resulting genotypic ratio among the offspring is 1 homozygous dominant pp to 2 heterozygous pp to 1 homozygous recessive pages. Phenotypically, both the pp and pp plants will have purple flowers, while the pp plants will have white flowers. This gives a phenotypic ratio of 3 purple to 1 white. Option A would be the result if all offspring were dominant. Option B correctly gives the 3-to-1 ratio. Option C is the ratio expected from a test cross. Option D is a modified ratio seen in some epistatic gene interactions, not in a simple monohybrid cross. The 3-to-1 ratio is fundamental to understanding inheritance patterns. Question 4. A group of students is conducting an experiment to investigate the effect of light intensity on the rate of photosynthesis in aquatic plants. They place sprigs of Elodea in test tubes filled with water and a small amount of sodium bicarbonate to provide carbon dioxide. They position the test tubes at different distances from a light source to vary light intensity: 10 centimeters, 20 centimeters, 30 centimeters, and 40 centimeters. They count the number of oxygen bubbles released per minute as a measure of the photosynthesis rate. Their results show that the bubble rate decreases as the distance increases. However, one student observes that the temperature of the water might also be affected by the distance from the light source, with the closer tubes being warmer. Which of the following modifications to the experimental design would best address this potential confounding variable? Is it? Option A. Place all test tubes at the same distance from the light source and vary the light intensity by using light bulbs of different wattages instead. B. Place the test tubes in a water bath maintained at a constant temperature to ensure that any differences in the bubble rate are due to light intensity alone and not temperature. C. Conduct the entire experiment in a dark room and use only artificial light, eliminating any variation from natural light sources. Or D. Measure the temperature of each test tube during the experiment and use statistical methods to correct for temperature differences after the fact. The correct answer is B. This question addresses the critical concept of controlling for confounding variables in experimental design. The student correctly identifies that temperature could be a confounding variable because it may vary with distance from the light source and is also known to affect the rate of photosynthesis. The ideal way to control for this is to hold the temperature constant across all experimental conditions. Option A changes how light intensity is varied but does not control temperature, so the problem remains. Option B, using a constant temperature water bath, is the best solution because it directly controls the confounding variable by keeping the temperature identical for all test tubes, allowing the independent variable to be isolated. Option C addresses light control but not temperature. Option D, measuring and statistically correcting, is a possible but less desirable approach than direct experimental control, and it requires more complex analysis. In scientific experiments, directly controlling variables is preferred over post hoc corrections. Question 5. A student is studying the properties of acids and bases. The student has an unknown solution and wants to determine if it is acidic or basic. They dip a piece of blue litmus paper into the solution and observe that the blue litmus paper turns red. Based on this single observation, what conclusion can the student draw? Is it? Option A. The solution is definitely an acid because blue litmus paper turning red is a standard test that indicates an acidic pH. B. The solution is definitely a base because bases are known to turn blue litmus paper red. C. The test is inconclusive, as litmus paper is known to be unreliable and can change color for many reasons, including temperature and salinity. Or D. The solution is neutral because neutral substances are the only ones that cause a color change in litmus paper. The correct answer is A. This question tests the basic knowledge of acid-base indicators. Litmus paper is a common pH indicator. Blue litmus paper is specifically designed to turn red in acidic conditions. Red litmus paper, conversely, turns blue in basic conditions. The observation that blue litmus turns red is a clear and reliable indication that the solution is acidic. Option A correctly states this conclusion. Option B is incorrect. Bases would turn red litmus blue. Option C is incorrect. Litmus is a standard and reliable indicator for this purpose. Option D is incorrect. Neutral substances do not cause a color change in litmus paper. Understanding how to use indicators is a fundamental laboratory skill. How many did you score out of 5? Let us know in the comments below. Also, tell us which exam we should cover next. If you found this video helpful, please like, share, and subscribe for more.